Welcome back to Mechanical Systems Design. So today we have a pretty fun video. We're going to be talking about how we use prototype testing in the design process. And we'll be looking at some high-speed videos of components being broken. We'll have some exercises. So you want to make sure you have a pencil and paper and a partner so you can get the most out of the experience. So why do we test functional prototypes? It's expensive in both time and resources. Well, it is the only way to know what will really happen when we try to use our mechanical system. So there's no way around it. And we need to do these tests to know whether things work. But since it's such a big investment, we'd like to get more information than that out of it. For example, there might be simple indications from our tests of how we can improve our design. Maybe the component breaks in a certain location, and we think, well, if I add more material there, it'll be stronger and better, which is good. But the most effective way of using the results of our prototype tests is to map those empirical results onto our simple models of our design. That will give us powerful tools to extrapolate into effective new candidate designs. For example, let's say we load our component and look at the way it deforms. And then we compare that to the way it deforms in finite element analysis or the implied deformation from our free body diagrams. If we see some differences, that can help us to make better assumptions about what the reaction forces will be, or use better simple models of stress for inverse analysis and back of the envelope analysis. And it may allow us to set up the computational problem better with more accurate constraints or more realistic loads. Those are all good ways that mapping these results back to our models can help us improve our design. We might also discover that there are phenomena we hadn't yet modeled, like we might see that our component fails in buckling rather than by yielding. And then we can go back and bring new models to bear on the problem. Today, we'll do a series of exercises where we look at the results of empirical tests and interpret them. And the problem scenario we're going to use is from a previous project in this class. And here's what students were designing. So in this problem, there is a heavy weight here tied to a rope. And this inset is a zoom in of this region. And that rope is tied to a clip that had two pegs sticking out of it. And on either side of the clip, you can see over here, are these plates that have lots and lots of threaded holes in them. And we had access to pegs with screws that could screw into any of these holes that we liked. And the students were supposed to design a component to be laser cut out of acrylic that would connect to those plates and connect to the clip, such that when we slid the component onto pegs on the support plates, and then we slid the clip into the component and then loaded it with that big heavy weight, the component would support the weight and not fall. And the clip would be held exactly in this position and orientation. So let's take a look at what happened when we actually loaded some of those components. And here's our first part. So you can imagine taking this part and sliding this hole onto a peg that's on that rigid support structure, sliding this hole into a peg that's on the other rigid support structure, then sliding the clip pegs into these two holes. And then as we lower the mass and then push down on it to give it a little extra force if necessary, there would be a big force on the clip downwards over here. And to get the most out of these functional prototype tests, we need to bring our intuition to bear on the problem. So the first thing I want you to do for all of these exercises is look at the part, imagine it being loaded, and make a prediction of what will happen when it gets loaded. And eventually when we pull hard enough on that rope, when the part fails. So take a look at it and sort of walk through those steps of mounting and loading the part and run a mental simulation. make a cartoon in your head of what will happen to this part. Visualize it. And just do that independently in the stillness of your own mind for a minute or two until you feel like you have an intuition as to what's going to happen and you have a, sort of an affirmative guess. Then discuss it with your partner a bit and then come back to the video. So you can pause now. All right, you have an idea of what's going to happen when this is loaded. Here is what it looks like when the component actually mounted in the test rig. I love these high-speed videos. There's so much texture and detail to it. So what we're going to do next is try to understand why this happened. And there's a lot here, but for this exercise, what I'd like you to focus on is the fact that this suit clip is at an angle. And I want you to try to think about, why is the suit clip at an angle compared to the intended orientation in the space? So just take a moment and you can draw or just think it through on your own for a minute or so, and then discuss it with your partner. So hit pause now. All right, do you have a guess, some reasoning as to why that might happen? Well, sometimes when we see something deflect significantly or move a lot from its original orientation, that's because it wasn't actually held in place. It's not under static equilibrium. And what we're going to find out in this case is that's happening. And you can see from these free body diagrams, which were produced by the designer, evidence that static equilibrium is not possible. So now I'd like you to take a look at these FPDs and see if you can figure out what is the argument that you can't get static equilibrium. So take a minute, push pause, trying to figure out it on your own and discuss it with your partner, then come back. All right, did you see it? So if we look at the free body diagram of the clip, we'll see that if we take moment balance about this second peg, both of these forces pass through that peg. So their lever arm about it is 0. But the weight, that force that's on that rope, well, that has a finite lever arm. It doesn't go through that peg. And so that will cause that peg, the whole clip to spin, right? You can't achieve static equilibrium with this free body diagram. And we can see that also from a free body diagram of the full system. So if we combine the clip and both of those components, and we call that our free body, actually the analysis can get a little bit easier. And this is one of those tricks in free body diagrams, what free body you choose. Well, we'll see that this is a 3-force member, just like we saw in some of the free body diagram video examples. So if we take a moment balance about point A or B or C, in all 3 cases, 2 of the forces will go through that point, while the third will have a finite lever arm, and we won't be able to get moment balance. So that can't happen. How would we use this information to improve our design? Well, we need to find an orientation of components where static equilibrium was possible. All right, here is our second component. And once again, what I'd like you to do is imagine sliding it onto those 2 support pegs, sliding the suit clip in, and then loading that rope that's offset from the pegs. And imagine, how will the part deform? And if you pull hard enough, how will it break? So run that mental simulation in your head for a minute or so until you've got a confident guess. Debate it a little bit with your exercise partner, and then come back. All right, you have an affirmative guess? Here's what the video looks like. And this is just an instant or so before the part breaks, and you can start to see the pattern of deformation in those arms. And here's what happens when we increase the load past the breaking point. You can see that the part is fracturing down here with that right arm intersects that rectangular section with that connects to the suit clip. So from here, what we'd like to do is engage those simple models. We'd like to try to map these results back into simple models of load and stress. So what I'd like you to do is look at this deformed shape and think about what it implies about the reaction forces at these support points and the qualitative loading experienced by these two arms. What's the appropriate simple model of loading, of stress, for those two arms? All right, so think that through. You can sketch stuff, then discuss it with your partner. It should take 2 or 3 minutes, and then come back. All right, you have some guesses? And as we do these things, we'd like to try to leverage the terminology and logic and engineering models we've been developing in our mechanics courses and in this design course. So the way I like to think about what's happening in this part is considering the deformation first, because that's the most obvious to me. And you can see that these arms are bending upwards. This one's bending sort of up, and this one's bending down. And wherever you have a bent shape, then you have bending loading, right? And we expect that the moment at these connection points will be small because they're round pegs and round holes. So probably there is a low bending moment here. That means there must be, there's probably a high bending moment there. This becomes a sort of cantilever beam scenario. And that is consistent with the way the component breaks eventually. You can see we get fracture at where the arm intersects there. That's where the bending moment should be highest. And our model of bending stress is sigma equals my over I, where m is highest. As long as we have this uniform cross section, the stress will be highest. And what does that mean about the loads at these points? Well, it looks like from the shape of the arm, the designer was thinking, oh, these will be axial loads. However, it has to be that there's a component, there's probably an axial component, but there must be a component that's orthogonal to the arm in order to get that bending, right? And so we've got a upwards orthogonal component here and a downwards orthogonal component on the left-hand side. If we look at the free body diagram this designer used, such as it is, we can see that indeed they were expecting those loads, I think it's clearest here, to be axial. And that turns out not to be correct. The finite element analysis did show us that there was bending if we look close. So if you look down here in the region where the part failed, we can see that classic bending pattern of stress, where on the bottom surface, we have very high stress. And as we move through the center of the part, the stress goes to 0 almost. And then when we continue on to the other edge, the stress gets high again. So this very high stress and then almost none, and then very high again on the other side. And that's that pattern of stress that we learned about in our solid mechanics course that occurs when you have bending. So the finite element analysis was also trying to tell us that this was an issue. So how can we use this information to improve our design? So think about the kind of loading that it actually experiences compared to what we thought at first. And what are the implications for how we could improve this component? And by improve it, I mean, how do we make it stronger for the same mass or keep the same strength and reduce mass? This is in these sort of mass optimal design problems. And there are two approaches that can work well. The simplest approach is imagine the part is kind of made of clay and then you're going to add a little bit here and take some out off over there. And you can iteratively do that over and over again till you get a nice even stress distribution. Another way of doing it would be to think about what are the biggest and most important decisions, the parameters that most affect performance, and how can I change those to make things better? So just take a minute and develop some guesses about how you might do this. You can pause, think it through for a minute or so, discuss with your partner, and then come back. Okay, so the straight ahead answer here might be, well, there's a big bending moment and it broke there, so I'm going to add material down here. And well, the bending moment's low up here, so I'm going to take away material there and get a tapered beam. And you can do that on both sides. And that would be a good improvement. Now, a slightly more sophisticated approach might be to say, well, the thing that's causing this high stress is bending. I don't like the bending. So how can I get rid of it? Well, one of the big choices we've made, maybe secretly in this design, is to make this arm line up with the center point between these two holes. And you can question that assumption and you could point it some other direction. We know that this reaction force isn't along this axis, but maybe if we change the axis of that arm, we could get the force to be aligned, and then it would be under axial loading, which might result in more favorable conditions. Okay, how about this part? Let's imagine that you set it on its pegs on that plate, you put in the clip, and then pull hard down on the rope. How will it deform, and then how will it break? Think about that. You can pause and take a minute or two. All right, do you have a guess? Well, here's a video of the component actually failing. It's a little hard to see here, but the component is, just before it fails, it's no longer in the plane of those support plates. It's actually bending out. So if you looked at it head on, it's kind of going like this. And then one of these lower legs is breaking out of plane. And this is a classic example of buckling. So as we increase the force, there's an unstable deflection. We'll learn more about this in a future topic reading. And that's causing that little piece to pop out and break. So this would be an example of prototype test that would tell us we need to bring a new simple model to bear on our problem. And to make it stronger in buckling, we could increase the area moment of inertia, as we'll talk about in a future topic reading. Okay, how about this one? We've got a truss design here, but a sort of truss shape, but cut out of all out of one piece of material. If you imagine sliding it onto the support pegs, putting in the clip here and loading that clip, how will it deform and how will it break? Once again, take a minute or two, pause, think it through, and then come back. All right, do you have a guess? Here's what actually happens. So once again, we have, it looks like maybe some out of plane buckling, like we saw in the last example, but the fracture is happening at lots of places simultaneously, and it's probably starting at one of those sharp internal corners, which are likely to be big stress concentrators. Now here is an image from the finite element analysis of this component that produced by the designer. And at this level, things seem to look okay. Remember that stress concentrations might not be evident if we use a coarse mesh in FEA. So if we look at what happens in our test and see that things are breaking right on these sharp internal corners, and we go back to our FEA and we're not seeing it yet, it tells us, okay, we could refine our mesh in those regions and get a more accurate result. But more broadly, I suppose there are other things we can do to improve the design. So why don't you take a moment think about what happened with this part, and then think about some simple changes you could make that would make it stronger for the same mass or lighter for the same strength. You have some guesses? Well, we have a pretty complicated geometry here with lots of sharp internal corners. Maybe we could get rid of those. The strength of trusses is that each element in the truss is a two-force member. But when everything's cut out of one piece of material, you don't necessarily achieve that same effect, especially with such small features. So maybe we could simplify things. That way we could better understand and analyze them and maybe get a better overall design. All right, next up, what will happen with this one? So we slide it onto the support pegs at those two upper points. We put the clip in the middle, load it by pulling down hard on the edge. If we pull harder and harder, how will it eventually break? Run your mental simulation. Pause and come back in a minute or two. You have a guess? All right, here's a video of what actually happened when we tested this component. So everything up here looked plenty strong, and here was where we had the weak link. Now, how did that happen? Well, if we go back and look at the finite element analysis of this component, we can see that a relatively simple load was applied here, where it looks that like the force was evenly distributed around the whole interior cylinder of that hole. And that means that half the force will be on the top of the hole and half will be on the bottom. And so in the real system, all the force will be on the bottom. And so this small lower section of material will experience twice the load as what's simulated here. And so our prototype test is pointing us to a way to improve our finite element analysis in this case. And of course, it could also point to a back of the envelope analysis, looking, say, at that cross section and using a simple model of axial stress, F over A, to better select this cross-sectional area on that little feature. All right, so those are some examples of how we can use prototype tests to map empirical results back into our simple models, better understand our part, and make decisions about how to improve it. Next up, we'll have a video on technical writing.